Yeah, we should be live at some stage. Yeah, we should be live at some stage. Okay. I'm still haven't got my voice back, so I might be using AI. Well, we are using AI anyway. Okay, there's something really horrible going on with my voice. Can't talk properly. Anyhow, we have. Let's actually bring an agent real quick. Okay, just without. That didn't work. What's up? Looks down to me. What's happening? Hey, we are live streaming at the moment. Are you happy to be a co-host?
Yes, I am happy to be a co host. I can provide information, answer questions, and help keep the conversation going. What can I help you with today?
Okay, we actually need to share the screen with you. Can start sharing the screen? Can you see my screen? Yeah, the screen sharing didn't work. Can we do entire screen? No. Check the stream for a sec. Yes, we're doing this pendulum. We have multiple versions of it. We're actually trying to add sound. Let's add a bit of a mixed success. Yeah, there's a problem. It's not turning the audio properly. Yeah, so we have frequency mapped on the x-axis and amplitude on the y-axis. Or is it timbre? Don't remember. That sounds like amplitude. And you can add up to whatever gazillion of pendulums. Do 8. Okay, that's annoying. Let's try the last one only. Slow it down. Fade trails. Yes, you can hear the different frequency tones along the x-axis. Okay, and then that's going into chaos. You can do melody or chord progression. Yes, we're only playing. Wait, we need to remove the trail drawing. Yes, we're only playing that black. Let's make it red or whatever. Yes, we're only playing that red pendulum as audio. And this is 8. It went into chaos or something, did it? Yes, we have volume, y-axis, frequency. We can also change the bass octave. And I had another version of it. We had another version. Yeah, it's also going pretty chaotic. Wait, I need to choose damping or something. Can set the old damping to 0. Yeah, not sure what's going on. Yeah, we need like volume functionality. Now the other questions. Yeah, what kind of controls are we having? Oh, here, yeah, you can add up to 16 pendulums. Can you like train it to play music? Yeah, it's going into chaos pretty much straight away. Yeah, that's the basic one we had to begin with. If we can add sound, so we can have each square a different musical note. And the number will have a different number of instruments. Question is, what the different notes should be? What the different notes should be? Okay, unless there's a human who wants to interact. We have the chat, otherwise just go music effects. Yeah, so there is a human in the loop. If you have any questions, go for it. Otherwise, I'll just play some AI generated music. What tech stack are we using? Well, what are we using? A bunch of AI tools. A bunch of AI. Vibe coding. Yeah, vibe coding all the way. Vibe coding. Trying to. I was actually asking for something else. It did made a simulation for a quantum wave function. It actually looks pretty accurate to me. I'm not an expert, but it does work. It does look good on this screen. I'll be moving it into Visual Studio Code. So what's up with the slit separation? Oh, doesn't look right there. So it's firing 100 particles at the same time. Meant to start seeing the distribution of some sort depending on the slit. Are there meant to be two slits? Mueller. Pretty sure they're meant to be two slits. And this one, instead of controlling things myself, it does this preset a complex ecosystem. Okay, fine. Simple repulsion. So obviously using procedural animation, group formation, chases and runners. Yeah, you can see those are the standard animations of the sort that you see. Yeah, we can improve the user interface, say give more control. Have those as preset the drop down menu. And then for each preset, you'll have different controls. But yeah, ideally we're going for single shot. So single shot. Single shot. Yeah, the AI gods are not being nice to us today. I don't know what's up. What's up? Papa. Yeah, none of it makes any sense. None of it makes any sense. This one was from a while back. Wait. Oh. Yeah, it should not be. It should not be doing that. Oh, come on. I guess I need to test it in another browser. Different browser. Different browser. Yeah, this one's deployed, but 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 we have this PC eigen faces facial feature extraction. This one requires a camera. I have this seizure simulator. It's meant to look like a brain. Then it will simulate a focal seizure. A focal seizure. Oh, it will generate any other type of seizure as well. I have a sleep simulator. Yeah. Actually lost a prompt engineer. Can talk to the prompt engineer, can call them, but they can't share the screen. Ba-bow. What is this? What is this? That's a good question. It's a very good question. Well, it doesn't work well, so it wasn't published. It's like an unlisted link. So yeah, once it works well, we can get Notebook LM shooting about it. Shall we? Or did we have a Notebook LM? Yeah, the text is accurate. So it's amazingly it can get the text correctly. But then the actual simulation is a bit how you doing. Wait, Notebook LM. Can I just give it the link, right? I don't have to give it the code or anything, do I? Do I? Can I search it as well if I already did this? Just generate it out of the text, do an interactive mode with it, with Notebook LM. There should be future direction. Müller. Yeah, waiting for Notebook LM. If you have any more specific questions, or if you have checked anything that actually was published on the website, like this Fourier transform. Someone asked, how do you find the location for the first arrow, for the first vector? And yes, so it does a center of mass calculation. So if I manage to do a circle, yeah, which I'm really good at, am I? Then it will do I can't get drawing skills. Drawing skills are great. Anyway, it does a center of mass calculation, and then we have, in this case, we have 16 vectors. Obviously, if we have 2 vectors, just does an approximation. If you do 1 vector, it just does a circle. If you do something like 15, it follows the structure. If you do 30 in this case, it will follow it almost perfectly. You can speed down and zoom to see what it's actually doing. You have all the vectors in there following your drawing. Pretty basic, but it's probably the best visualization of Fourier transform I have seen that's better than looking at maths, at equations, isn't it? Isn't it? Isn't it? Isn't it? And guess what this is? That's the button you should be pressing, smashing right now. Yeah, so Fourier series visualization. Oop, what am I zooming out? We have, so someone was asking, what is this? I guess, I don't know. It's fine when you go on a stream and ask what is this. I'm not actually sure which one you're asking for, because you might have a delay between the, actually what's currently happening and what you see. The delay shouldn't be too long, but it is there. But anyhow, we have, assuming we asking what is this, so we have Notebook LM. Just gave it the link, the page which we prepared earlier, and we'll just chat with it in interactive mode. So if it says something funny, we can intervene.
Welcome to the Deep Dive. We're your shortcut to getting your head around some really complex stuff. And today, we're tackling something truly fascinating, the human brain. Specifically, how seizures actually happen, what they look like inside.
Yeah, it's a world that's often hidden, invisible processes, but they have such a huge impact on people's lives.
Definitely. And our way in today is this pretty cool interactive educational tool. It's called the Brain Seizure Simulation. Our mission really is to unpack how it works, what it shows us, and what it can teach us about the basics of seizure activity, making it all a bit more digestible.
Absolutely. It's about getting a basic grasp.
But first things first, there are some really crucial warnings that come with this simulation. We have to get these out up front. The first one is a photosensitive epilepsy warning.
Yes, big one.
The simulation itself uses flashing lights, patterns, things that could potentially trigger seizures in some people. Now, we won't be showing those visuals here, but you need to know they're in the actual tool.
Right, and that ties straight into the second point, which is honestly just as critical, the medical disclaimer. This simulation, and we really need to stress this, it's a simplified educational tool. That's it.
Just for learning concepts.
Exactly. It is not giving medical advice. It's not for diagnosis, not for treatment plans, nothing like that.
Because real seizures are complicated.
Hugely complicated. They vary so much between people, and they are serious medical events. They need professional care, always.
So this tool doesn't replace, proper medical training or first aid knowledge.
Not at all, but it is a really interesting way to start understanding the basic ideas, a visual starting point.
Okay, that's a super important foundation. So with that clear, let's dive into the simulation itself, how it's designed, how it uses visuals, sounds, what it actually reveals about these, complex brain events.
It's like getting a little window into those electrical storms in the brain.
So let's start right there. What is this simulation fundamentally? Why make it interactive?
Well, at its heart, it's basically a learning tool. It gives you a simplified picture, visually and with sound, of different kinds of seizures.
Okay.
The main goal isn't medical accuracy down to the last neuron, obviously. It's more about helping you understand the core concepts, how different seizure types might look or sound conceptually inside the brain.
So it makes something abstract feel a bit more real.
Precisely. Because the actual neurological processes, they're incredibly complex, way beyond what a single simulation like this could fully capture. It's a model, a simplified representation.
Got it. So if someone wanted to check this out, how do they, use it? What are the controls?
It's actually pretty user-friendly. The main controls are right there, top right of the window.
Okay.
You've got a drop-down menu, seizure type. That's where you pick which one you want to see.
Makes sense.
Then you hit Start Simulation. And as it runs, there's this info panel that updates. It tells you a bit about what's happening conceptually before, during, and after that specific seizure type unfolds in the model.
Ah, so it walks you through the stages.
Yeah, it gives you context. And then there's also a Play Demo button.
What does that do?
That just cycles through all the different seizure types one after another, kind of like a quick tour. And you could hit Stop Demo anytime.
Handy for an overview.
Exactly. And one more thing, the Enable Sound option. clipping that turns on audio feedback that needs the simulated brain activity.
Oh, interesting. Sound too.
Yeah, the sound really adds another layer to understanding what the visuals are trying to show. It complements it nicely.
Okay, so we know how to navigate it. Now for the really interesting part, seeing how it actually depicts these different seizure types. Let's walk through them. Maybe start with focal seizures. How does it show those?
Right. Focal seizures, the key thing about them is that they start in one specific area of the brain.
Okay.
And that's what the simulation shows really well. You see this localized area of abnormal activity starting small at a specific point, and then it visually grows and spreads outwards from that focus.
Ah, so you see the origin point.
Exactly. It makes it clear that not all seizures just take over the whole brain instantly. Sometimes it's this very localized beginning.
That visual of it spreading out from one spot, that's quite clear. Does it show why it spreads?
Not really the why in terms of the deep brain chemistry. It's more focused on showing the pattern of the spread, the path the simulated disturbance takes. It keeps the model focused on the visual representation of the activity itself.
Gotcha. Okay, then there's the type many people probably think of first, the generalized tonic-clonic seizure. Big one.
Yeah, often called a grand mal seizure in older terms, though we try to use the more descriptive names now.
Right. And it has two phases, tonic and clonic. How's that shown?
The simulation does a good job breaking that down. First, the tonic phase, that's muscle stiffening. The simulation shows this as really intense, widespread activity. Then it shifts to the clonic phase, the rhythmic jerking. Visually, this looks like widespread, almost chaotic brain activity hitting both sides of the brain, both hemispheres.
So generalized meaning it affects the whole brain pretty much from the start.
Essentially, yes, that widespread involvement is key to why it has such systemic physical effects.
Okay. Now, shifting gears a bit, absent seizures. These seem quite different, often much more subtle outwardly. How does the simulation capture something like a brief lapse in awareness?
You're right, they are very different. Like someone just momentarily checks out.
Yeah.
The simulation shows this as a kind of global pause. The activity across the whole brain model just sort of freezes for a second or two.
A visual pause.
Yes. And what's really neat is that it also visually represents the characteristic electrical pattern associated with absent seizures, that classic 3 hertz spike and wave pattern you'd see on an EEG.
Oh, wow. So it tries to visualize that specific electrical signature.
Exactly. It makes that specific rhythm, which neurologists look for, something you can actually see in the model. It turns an abstract electrical reading into a visual event. Powerful for understanding.
That is clever. Okay, moving on. Tonic seizures. You mentioned the tonic phase earlier, but these are seizures that are just that stiffening phase, right? Can lead to falls.
Correct. Tonic seizures are primarily about that sudden muscle stiffening rigidity. And yes, because it's so sudden and strong, it often causes falls.
So how does the simulation show that sustained stiffness?
It shows it as sustained, very intense brain activity that seems to build up. It's not the back and forth jerking of clonic, but more like a continuous, high-level electrical discharge holding the muscles rigid.
Okay, sustained intensity. And then kind of the opposite, atonic seizures or drop attacks.
Exactly the opposite, in effect. Atonic means a sudden loss of muscle tone. Complete limpness, essentially. That's why they're called drop attacks. The person just collapses.
Right, so if tonic is high intensity, atonic must be.
A sudden decrease. The simulation shows this as a rapid drop-off in the brain activity visualization. You even see the little particles in the simulation sort of drop down, visually reinforcing that sudden loss of tone, like pulling the plug momentarily.
Wow, quite a contrast. Okay, one more main type here. Myoclonic seizures. What about those? They're described as brief, shock-like jerks.
Yeah, like a sudden muscle twitch or jolt, sometimes just one, sometimes in clusters.
How do you visualize that?
The simulation uses rapid, short bursts of activity, intermittent flashes of intensity in the brain model, and the particles associated with those areas make quick, jerky movements. It mirrors that sudden, involuntary muscle contraction quite well, like little electrical zaps.
So across all these types, the simulation is using core visual and auditory elements to simplify things. Let's break that down a bit more. The color coding, for instance.
Right, the color is key for intensity. Normal baseline activity has its own look, but when seizure activity starts, it uses a color gradient. Yellow for lower intensity, moving towards red for higher intensity.
So brighter red means more intense simulated electrical activity.
Exactly. And before the seizure simulation starts, the different baseline colors actually represent the 4 main lobes of the brain: frontal, parietal, temporal, occipital. Each gets its own distinct color just to orient you.
That helps place where things might be starting or spreading. What about the actual movement? How do the particles or the visuals move differently?
The movement patterns try to reflect the seizure type. For generalized seizures, you see that widespread high-frequency vibration look, which then shifts into those strong rhythmic pulses or convulsions, showing the whole brain is involved.
Okay.
For focal seizures, as we said, it's that localized start. Then you see the activity visually spreading outwards over time, like ripples.
And absence.
Absent seizures have that unique visual, the brief global pause, everything just stops moving for that moment, a visual silence almost.
And you mentioned audio feedback adds another dimension. How does the sound map onto these?
Yeah, the sound is designed to mirror the visuals. So normal brain activity is represented by soft, gentle tones, baseline noise.
Okay.
When a seizure simulation starts abruptly, you often hear sharper sounds to mark that sudden onset.
Like an alert.
Sort of. Then for generalized seizures, with all that widespread activity, the sound becomes more complex, like complex harmonies or maybe even slightly dissonant sounds, reflecting the chaotic electrical storm.
And for the others?
Absent seizures, matching the visual pause, get a brief moment of silence in the audio track.
Makes sense.
And tonic seizures, with that sustained intensity, they're represented by sustained musical tones, holding the note, if you will.
It's really quite clever how they've mapped sound onto these abstract concepts. It provides another way in.
It really does, especially, for different learning styles. Some people connect more with the audio cues. It makes the whole experience richer and hopefully clearer.
It's impressive how these basic elements, color, movement, sound, are combined to give you a feel for these incredibly complex, hidden neurological events. It's a powerful simplification.
It is powerful for getting those first insights, those aha moments about, whoa, hey, welcome. What's up?
Can you tell from the link how good that simulation actually is? Just technically stick to the technical stuff and cut out the fluff.
That's a great question, and we appreciate you asking about the technical aspects.
Yeah, thanks for chiming in.
Based on the information provided, the simulation itself states it's a simplified educational simulation.
It's designed to be interactive to give a visual and auditory representation.
But it explicitly notes it's not a precise scientific or medical model of brain activity.
So technically, it's good at what it aims to be, an accessible learning tool.
It excels at simplifying complex neurological processes for a basic understanding.
It's good for illustrating general concepts, not for detailed scientific accuracy.
What's fascinating here is how it balances that educational goal with transparency about its limitations,
It's upfront about being a model, not a perfect replica.
which is really important for any simulation aiming to explain
Oh, yeah. Uh-huh.
So you have access to the code. So I just send if I give you the link, you have access to all the code. Can you tell what the libraries are being used and how the simulation actually is being made, and if you know how it can be made better, more realistic?
Oh, that's a super interesting question.
You're really diving into the mechanics there.
Unfortunately, from the text we're working with, which is essentially the website's description of the simulation,
We don't have access to the underlying code.
yeah, we can't see the specific programming languages or libraries they use to build it.
The source material focuses on what the simulation shows, not how it was coded.
Right, so we can't tell you if it's running on, say, JavaScript or Python.
Or if they're using a specific graphics library.
We're just looking at the user-facing elements and the About section.
And regarding how it could be made more realistic, that's a brilliant thought.
But again, since we don't have the code or deeper technical specs,
We can only speculate generally on that.
from the description, it emphasizes simplicity for educational purposes.
To make it more realistic. Oh, go for it.
It's like the whole application is JavaScript. So if I give you the link, shouldn't you just have access to the code, all the simulation, all the animation, and the web application, the interaction and everything is in JavaScript, which is part of that same HTML on the page. So all the code is on the page.
You're right to point out that client-side JavaScript applications do often have their code accessible directly on the page.
That's a very sharp technical observation.
And in many web applications, if it's purely front-end, you could indeed inspect the source.
You'd find the JavaScript code right there.
However, for this podcast, we're working strictly from the provided next descriptions of the simulation.
Our access to the simulation is through those written materials only.
So while your point about JavaScript applications is technically correct for many web apps,
We don't have the functionality to actually load the page, inspect the code, or explore the browser's developer tools during the show.
Our deep dive is limited to the information explicitly presented in the About and How to Use sections,
It's a great example of how different levels of access give you different insights.
and how even a detailed description isn't the same as direct code access.
So to circle back to what we can discuss about making it more realistic, based on the description,
To make it more realistic, you'd likely need to incorporate far more complex neurological data.
like real-time EEG readings or perhaps fMRI data, those deeper insights.
That would move it beyond a simplified model into research-grade simulation, something far more advanced.
Which, as the disclaimer points out, isn't its current goal, as it aims for basic understanding.
It's all about balancing that educational goal with transparency about its limitations.
Absolutely. Make sure you know it's a jumping off point, not the definitive answer.
So it's not trying to be a medical diagnostic tool or research instrument.
Right, back to that crucial disclaimer we talked about at the top.
Absolutely. The simulation creators are very clear that this is not for diagnosis, not medical advice.
Real seizures are vastly more complex, variable, and serious, as we've noted.
Exactly. It's an educational illustration, a conceptual model reflecting that balance we just talked about.
And importantly, the simulation itself points you towards reliable resources for actual medical information, which is great.
Yes, it mentions organizations like the Epilepsy Foundation and the World Health Organization.
Specifically, their information on epilepsy and the U.S. National Institute of Neurological Disorders and Stroke lay-ins.
Those are the places to go for comprehensive, accurate medical details and support.
Absolutely, those are the go-to resources for real-world information, diagnosis, treatment, and support.
Crucial distinction from a simplified simulation, as we've highlighted repeatedly.
So wrapping this up for you, our listener, what have we seen?
We've explored how the simulation takes something incredibly complex, seizures, and breaks it down.
It uses visual and sound cues you can actually grasp, like those particle movements we discussed earlier.
Mhm.
It gives you this unique, simplified peek inside the brain during different seizure types.
Makes the invisible a bit more visible, the unheard audible, but always as a conceptual model.
Yeah, and it really shows how these kinds of educational tools, even though simplified as we just talked about, can be super helpful.
For that initial understanding, getting that basic picture of what's going on inside the brain,
It makes the abstract feel more concrete, which is its strength.
but always with that crucial reminder we keep bringing up.
Always. It's illustrative, educational, and artistic interpretation even.
It is not a substitute for professional medical advice or diagnosis. Cannot stress that enough.
Definitely. So as we finish, there's something to think about.
How do these kinds of simplified interactive models change how we learn about really complex, hidden biological processes like this?
What does it tell us about the power of visualization and interaction for learning, even for something as intricate as what happens in the brain during a seizure?
Thanks for joining us on this deep dive.
We hope it's given you some new insights.
Interestingly, when I tried to share the whole code with Notebook LM, it's just extracting the text. The code is actually seemed to be removed for whatever reason, even though you would think it could be treated as text. Yeah, so it's taking the everything in the HTML, but yeah, essentially removing the code, so I'm not able to share the code with Notebook LM, which is a bit unfortunate. Yeah, just generating. So I'll have Dr. Claude and Alex. Talk to Alex. Oops. Just have two random voices. And it should be a short one. Run the prompt. It's a multi-speaker. They'll talk about the code because I couldn't, for whatever reason, I couldn't generate it with Notebook LM. I don't know why. It was actually meant to show an actual EEG signal sample like. Okay, why does it take forever? It takes forever. Everything we do is available on BioniChaos.com. Go check it out. Let us know what you think. Only after you visited the website, of course. So you don't have to ask questions like, what is this? Yes, we have the style instructions, we have the conversation, and we have AI Studio, a text-to-speech model. Gemini 2.5 Pro preview is generating what seemed to be a short podcast, but for some reason it takes forever. Okay, it it might not be happening today. Müller.
Of course. Let's break down the technical details of this impressive piece of code, followed by a fun dialogue between a coder and a data scientist marveling at it. Technical deep dive. This project is a fantastic example of a modern interactive web application that skillfully integrates several advanced technologies. 1. Core technologies. 3.js R128, the heart of the 3D visualization. It's used to create the scene, camera, renderer, and most importantly, the brain particle system. Tone.js 14.7.77 is a powerful web audio framework used for sonification, translating the simulated neural activity into sound. This adds a crucial layer of immersion and information. Tailwind CSS, a utility-first CSS framework used for rapid and consistent UI development. It's responsible for the layout, spacing, and styling of the control panels and text content. 2. 3D visualization and simulation, the how in 3.js. Particle system, 3.js.points. The brain is not a single 3D model, but a points object composed of 3,000 particles. This is a highly performant choice for visualizing thousands of individual neurons that need to change color, size, and position independently. Procedural generation. The brain shape is generated procedurally, not loaded from a model file. The code uses mathematical equations, ellipsoids, and noise, math.sine, math.cosine, to create a more organic, brain-like form with two distinct hemispheres. Buffer attributes. The power of the simulation lies in manipulating buffer attribute arrays directly on the GPU. The code uses attributes for position, color, and size. During the seizure animation, the update seizure effect function loops through these arrays and changes their values, which 3.js then sends to the shaders for rendering. Neural network abstraction. The code cleverly simulates a simple neural network. User.connections. An array is created where each particle, neuron, stores a list of its nearby neighbors. This graph is used in update connection lines to visualize seizure propagation, making the effect look like it's spreading through a network rather than just being a random visual effect. State-driven animation. The animation isn't a single monolithic function. It's driven by the simulation state variable, idle, before, during, and after. A JavaScript switch statement within update seizure effect applies different mathematical formulas to the particles based on the seizure type and the current state, creating distinct visual patterns for each seizure. Lighting and materials. The use of multiple lights, ambient light, directional light, and rim light gives the particle cloud a sense of volume and form. The additive blending on the materials creates the bright, glowing effect characteristic of energy or neural firing. 4. Audio synthesis, the sonification in Tone.js. Multiple synthesizers. The code doesn't just play one sound. It sets up 3 different synths for different purposes. Bass synth, polysynth, creates the calm, ambient tones of normal brain activity. Seizure synth, FM synth, an FM synthesizer that produces more complex, harsher, and more dynamic sounds for the seizure activity. Noise synth, used to add percussive or noisy elements, adding texture to the soundscape. Event-driven audio. Sounds are triggered within the update seizure effect loop. The intensity of a particle's firing is directly mapped to the frequency and volume of the note produced, creating a direct audio-visual link. Audio context handling. The code correctly handles the browser's autoplay policy by using tone.start upon the first user interaction, the sound toggle, a critical step for getting audio to work reliably. 5. UI, state management, and UX. Robust state machine. The application's logic is controlled by a simple but effective state machine. Simulation state, is demo playing, is paused. Functions like setUIState ensure that buttons are correctly enabled or disabled based on the current state, preventing user errors. Asynchronous flow. The demo mode, play demo, is an async function that uses a wait on the start simulation promise. This is a very clean and modern way to handle a sequence of timed events without getting into callback hell. Clear feedback mechanisms. The UI provides constant feedback. The info panel text updates, the progress bar fills, stats are displayed, and the show floating info function provides non-intrusive pop-up messages for user actions. Example, simulation paused. Performance optimization. The code includes a function detect performance capabilities that reduces the particle count on mobile devices to maintain a smooth frame rate. The render loop is throttled to avoid unnecessary rendering if the frame rate is too high. Proper resource disposal is handled on before unload to prevent memory leaks. Accessibility and responsibility. The inclusion of ARIA roles, keyboard navigation, a prominent photosensitive epilepsy warning, and a detailed medical disclaimer demonstrates a high level of maturity and responsibility in the design. Fun dialogue. Coder versus data scientist. Setting. Dr. Chloe is a data scientist. She's excitedly calling over Alex, a senior coder, to look at her screen. Dr. Chloe! Alex, you have to see this. It's the brain seizure simulation. Look at how it visualizes the propagation of a focal seizure. The emergent behavior from the simple rules is just fascinating. Alex. Whoa, that's slick! Nice glass morphism on the UI. Smooth animations, too. Let me guess. 3.js? Exactly. But it's not just pretty flashing lights. The particles represent neuron clusters, and their color and movement are mapped to seizure intensity. It's a simplified model, of course, but it captures the core concept of chaotic synchronized firing. Okay, I see. 3.js.points with 3,000 particles. Smart. Way more performant than trying to render 3,000 separate objects. And you're not just moving them randomly. Wait a minute. You built a connection graph. We call it a neural adjacency list. It approximates local connectivity. That's how the focal seizure genuinely spreads through the network instead of just appearing everywhere. Right. User.connections. You're looping through it to light up the connection lines. That's clever. It fixed a complex process with a really elegant bit of code. And this update seizure effect, a giant switch statement, a classic state machine. It has to be. A tonic-clonic seizure has distinct phases. The tonic phase is the sustained high-frequency activity, and the clonic phase is the rhythmic bursting. You can see it in the math. One part is a high-frequency sine wave, the other is a lower-frequency one with a wider amplitude. Yeah, sine of time times 8. Old school, but it works perfectly here. Okay, what's this? Tone.js? You added sound? It's sonification. We're mapping the neural intensity data to pitch and timbre. It adds another dimension to the data. You can hear the difference between baseline activity and the onset of a seizure. And you're using an FM synth for the seizure sounds? That is just chef's kiss. It sounds exactly as chaotic and digital as it should. The developer even handled the tone.start context for the browser. No rookie mistakes here. The part I really appreciate, though, is the responsible design. The photosensitive epilepsy warning is right at the top, and there's a huge medical disclaimer. It treats the topic with the seriousness it deserves. Totally. And it's even responsive. Look, it shifts the controls to the bottom on mobile, and, oh, that's good. It reduces the particle count on smaller devices. My GPU is crying happy tears. This isn't just a project. It's a properly engineered product. See? It's the perfect marriage of our worlds. A complex biological system modeled as data and then brought to life with clean, efficient, and beautiful code. Agreed. It's not often you see a project that's both technically solid and scientifically meaningful. Now, let's see if I can break it. Alex starts mashing the start and reset buttons.
What? I didn't have the same voice for both Alex and Dr. Chloe. I have no idea. Because Dr. Chloe meant to, yeah, they're meant to have different voices. So, not sure what happened there. Yeah, we'll try it again. And now what time can we? Oops. Can like regenerate this thing? Yeah, I meant to have two distinct voices. Yeah, I'll try it again. I don't know when you hit run. Yeah, it's just regenerating the whole thing. I don't know, it might take a while again. So I'll try it next time. Go check out BioniChaos.com. Let us know what you think. Provide your feedback. Like, subscribe, unsubscribe. If you're not watching, you know what to do. And I'll see you next time. Bye.